This research paper delves into the fine-tuning of transformer architectures on the Semantic Textual Similarity Benchmark (STSB) dataset, employing various models and sizes. The approach integrates outputs from multiple transformer models with handcrafted features as inputs for gradient boosting algorithms. It also entails fine-tuning the regression head followed by end-to-end fine-tuning. The paper delves into related work, experimental setup, results, analysis, and future improvements. The paper discusses the application of deep learning models and boosting algorithms in semantic textual similarity tasks. It highlights the use of pre-trained language models such as BERT, RoBERTa, BERT, and DeBerta v3, which have shown promising results in various natural language processing tasks. The paper also explores boosting algorithms like AdaBoost, XGBoost, and LightGBM for their ability to learn from tabular data and resist overfitting. The experimental setup involves using the Semantic Textual Similarity Benchmark dataset, comprising texts from image captions, news headlines, and user forums collected between 2012 and 2017. This dataset contains 5,749 examples in the trained split, 1,500 in the dev split, and 1,379 in the test splits. The task is a regression task with labels in the 0-5 range. The metrics used for evaluation are Pearson's correlation coefficient and Spearman's rank correlation coefficient. The paper provides a detailed examination of the dataset, noting that some datasets only appear in certain dataset splits. It also presents tables summarizing the hyperparameters chosen for the final models using mean-squared error and cross-entropy error. These hyperparameters include batch size, learning rate, and weight decay, which vary across different models and fine-tuning methods. The paper concludes by emphasizing the importance of understanding the strengths and limitations of different models and algorithms in semantic textual similarity tasks. It suggests that while pre-trained language models have achieved state-of-the-art results, there is still room for improvement, particularly in terms of efficiency and adaptability to different datasets. The research paper discusses the fine-tuning approach and boosting methods used in transformer models for sentence similarity prediction. It involves two stages: fine-tuning with a frozen base model followed by end-to-end fine-tuning. Hyperparameter optimization was conducted using population-based training and hand-tuning, with the final selected hyperparameters provided. Two problem framing approaches were explored: regression and binary classification, with each model fine-tuned for 10 epochs and utilizing early stopping, cosine annealing scheduler, and atom optimizer with weight decay regularization. The boosting process involves combining the outputs of transformer models with handcrafted features focused on sentence structure, including character, stopword, token, verb, adjective, overlapping token, and overlapping lemma counts. The results of these experiments are presented, comparing the performance of different transformer models under both regression and binary classification problem framing. Models tested include BERT, RoBERTa, BERT, and DeBerta v3, with varying sizes. Performance metrics are provided for train, development, and test sets. Baseline results using cosine similarity, linear regression, and support vector machine are also presented for comparison. The research paper presents the results of experiments on sentence similarity tasks using transformer-based models and boosting algorithms. Tables 7 and 8 display the results of using mean-squared error and cross-entropy error transformers, respectively, with 2 and 3 transformers. The boosting algorithms, namely AdaBoost, XGBoost, and LightGBM, achieve improved performance when using multiple transformers. LightGBM and XGBoost outperform AdaBoost, with LightGBM performing slightly better than XGBoost in most cases. Table X presents the results of using cross-entropy error transformers with a stratified cross-validation split, comparing partial fine-tuning and end-to-end fine-tuning approaches. The results indicate that end-to-end fine-tuning achieves better performance than partial fine-tuning, with DeBerta v3 large achieving the best results. Table X displays the boosting results using cross-entropy error transformers with a stratified cross-validation split, again comparing 2 and 3 transformers. The results show that the boosting algorithms achieve improved performance when using multiple transformers, with LightGBM and XGBoost performing slightly better than AdaBoost. The authors explain that the inclusion of certain features, such as verb counts, overlapping tokens, and lemmas, helps capture semantic and syntactic information in the text, which in turn improves the performance of the boosting algorithms. The choice of transformers is also discussed, with the hyperparameter optimization procedure selecting a combination of different transformer architectures rather than combining smaller and larger models of the same architecture. This is attributed to different architectures excelling on different examples. The paper delves into the performance of ensemble models in predicting semantic similarity scores for sentence pairs, highlighting issues related to label distributions across different dataset splits and edge-of-range predictions. Despite achieving better development set results, the ensemble models perform worse on the test set compared to single transformer models. This discrepancy is attributed to differences in label distributions between the train, development, and test sets, as confirmed by a Kolmogorov-Smirnov test. To address this issue, the authors retrain the best ensemble model and corresponding transformer architectures using stratified cross-validation with binning. This approach reduces the differences between development and test correlation coefficients for the best performing model from 0.012, 0.013 to 0.004, 0.007. Furthermore, the authors observe that their ensemble models struggle with predictions near the edge of the prediction range, as shown in scatter plots. They identify that sentences with high errors often contain more filler words, leading them to calculate the Jaccard index of lemmas for paired sentences both with and without stop words. The densities of examples with correct and incorrect predictions are visualized in Figure 1, providing insights into the model's performance. The table presents the mean absolute error between predictions and labels in different label spans for two ensemble models: light GBM with mean squared error, MSE, and light GBM with cross-entropy, CE, error. Both models struggle with predictions at the edge of the prediction range, with the MSE ensemble model performing worse than the CE model. The combination of modern transformer architectures like BERT with traditional ensembling algorithms improves performance on the development set. However, the models generalize poorly to the test set, attributed to the predefined dataset splits. Analysis of the best performing ensemble models reveals that the number of meaningful lemmas is a good indicator of whether an example is difficult. These models are less accurate on the edges of the prediction range. Future work includes investigating the effect of ensembling when using only small transformer models, extending this idea to sentence embedding models like SentenceBERT, and employing ensembling to specific textual domains.